Entire societies have vanished. No written word left behind to say why. We're going to read their story now, from a library made of ice. By the end, you'll see human history through a different lens. One that shows the invisible forces, the ones that took down mighty empires. There are layers of ancient pollution trapped in a glacier. What do they tell us about the fall of Rome? A speck of volcanic dust. It can pinpoint the exact year, the year a brilliant civilization started to crumble. We're going to decode warnings from a frozen archive. We'll see how climate catastrophes, written in ice, solved mysteries. Mysteries archaeologists couldn't solve. So what do you believe? What's the greatest threat to a thriving civilization? This ancient ice is like a time capsule, more valuable than gold. In the most remote frozen places, scientists like Lonnie Thompson drill deep into glaciers. They pull up these pristine records. Every year, a new layer of snow falls. It captures a snapshot of the atmosphere. That snow compresses under its own weight. It traps tiny air bubbles. It traps dust from distant deserts, ash from volcanic explosions, chemical signatures from the air people breathed, year after year. Century after century, these layers stack up. They create a frozen library, and we can read the pages now. The process is one of extraordinary precision. You drill down, you pull up a core, and you can look back through time. You can count the layers like counting rings on a tree. You can date events with astonishing accuracy. Sometimes down to a single year, but what are they reading? They analyze oxygen isotopes locked in the ice. Those isotopes act as a global thermometer. They tell us whether a year was warm or cold. They measure the amount of dust. That's a sign of how dry and windy a period was, and they look for sharp spikes in sulfate. That's the chemical fingerprint of a massive volcanic eruption. An eruption that spewed ash and gas high into the stratosphere, that cooled the entire planet. This isn't guesswork, it's a direct physical record, a record of the planet's past climate and atmosphere. An ice core from Greenland can tell us about droughts in North America. A core from the Andes holds clues to rainfall patterns, the patterns that sustained ancient South American empires, or the patterns that failed them. These frozen archives give us something written history often cannot, an unbiased logbook, a logbook of the environmental stage, the stage upon which human civilizations rose and thrived and faced their greatest challenges. With this time machine in hand, we can return to those silent ruins, and we can listen to the story the ice has preserved. In the frozen library, the first chapter looks like an economic report, except it's written in ancient pollution. Up in the Greenland ice sheets, they found traces of lead and copper. These metals didn't come from the ground. They traveled on the wind for thousands of miles. They're chemical ghosts, the exhaust fumes of empires that are gone. Think of a time before global markets, before instant communication, but the air was a connecting thread. When Roman mines in Spain or Britain were at full capacity, extracting silver from lead ore, that process released huge amounts of lead dust into the sky. That dust was carried north by weather patterns. It settled year after year on the clean snow of Greenland. Then it was buried, and it waited. By measuring the lead concentration in each annual layer of that Greenland ice core, scientists can chart Rome's economic heartbeat. The spikes are clear. During the peak of the Roman Republic, and later under emperors like Trajan, the lead pollution in the ice soars. That matches historical records of intensive silver mining. Silver was needed for the denarius, the coin that fueled Roman trade, paid its armies, ran its administration. The ice tells us when Rome was rich, confident, expanding. Its industrial breath reached the Arctic, then the record turns. Lead levels plummet dramatically. These sudden drops line up with periods of crisis. The civil wars that tore the Republic apart, the Great Antonine Plague that swept through, causing massive loss and halting industry. Even the slow unraveling of the Western Empire shows a long, declining trend in that faraway ice. When Rome coughed, the ice in Greenland recorded the silence. A parallel story is told by copper in ice cores from other parts of the world. In the mountains of Tibet, ice has preserved the industrial rhythm of ancient China. The rises and falls in copper pollution match the dynastic cycles. Peaks happen during the prosperous, unified eras of the Han and Tang dynasties, when coinage and bronze production were at their height. The valleys correspond to times of fragmentation, conflict, collapse, when central authority broke down and mines fell idle, so that's the first link. The economic health of a civilization, its industrial ambition, its stability, isn't just in its ledgers or monuments. It's inscribed in the global atmosphere. And it's preserved with perfect, silent fidelity in ice. We're not reading interpretations or biased histories. We're reading the physical residue of their daily work. And when that work stopped, the ice recorded the end of an era. It's a stark chemical obituary, but that's only the first clue. The ice holds more than just the smoke of industry. It holds the ashes of catastrophe. The ice holds more than just traces of industry. There's another kind of evidence, dust, fine layers of dust carried on the wind and settled in the ice. To read that record, you have to picture the land it came from. Dry earth, rivers that are just cracked clay now, fields that turn to powder. When the rain stops and the wind starts, that soil lifts into the air. It travels. Scientists drill into glaciers in the Andes. They pull up ice cores. In the clear ice you see bands. Some bands are clean. Those were wet years. Others are dark, gritty with dust. Those were the drought years. By looking at how much dust is there, and even the size of the particles, they can tell how bad the dry periods were. Bigger, heavier dust means strong winds carrying material from nearby. Finer dust comes from farther away. Together, it's a record of atmospheric suffering. One story from this dust comes from Lake Titicaca. The Tiwanaku civilization was there for centuries. They were engineers. They built raised fields and canals to farm the high plains. Their society was complex. Then, around the year 1100, something shifted. The ice cores from nearby glaciers show it clearly. For decades, the dust layers get thick. And they stay thick. This wasn't just a dry spell. It was a mega-drought. It lasted generations. The analysis shows a slow disaster. The long drought dropped the lake's water level. The agricultural system, built for a specific climate, started to break. The fields dried up. The canals filled with dust. The food supply, the foundation of everything, fell apart. What happened next wasn't a sudden collapse. It was a slow dispersal. Communities broke apart. People left the ceremonial centers looking for water, for food. The social order, built on plenty, dissolved under the sun and the constant wind. So that's the second clue from the ice. It links environmental stress directly to a society's fragility. The dust layers are a physical log of hard years, years when the sky itself worked against human plans. It shows climate wasn't just a setting, it was an actor. A civilization can be perfectly adapted to its world, but if that world changes in a way its systems can't handle, even an advanced society faces a deep challenge. The ice tells us the biggest threats aren't always the ones you see coming. Sometimes they're the ones you breathe. The most dramatic things in this frozen record are written in acid. Scientists find these sudden spikes in sulfate deep in the ice. It's the mark of a cataclysm, a volcano erupting on a scale that changes everything. When a volcano explodes with that kind of force, it sends a cloud of ash and sulfur dioxide up into the stratosphere. That sulfur turns into tiny particles. They spread around the whole planet, forming a veil that blocks the sun. It turns the planet's thermostat down, not for a season, but for years. A volcanic winter, think about a year without a summer, then another one and another. Crops fail under cold, gray skies. The harvest freezes right in the field. The growing season just disappears. For a society already strained, maybe by drought or conflict, this isn't just a bad year. It's a breaking point. The ice cores give us the dates. One of the biggest spikes is in ice from Greenland and Antarctica from the year 536. The sulfate layer is huge. It points to an eruption of almost unimaginable size, probably in the tropics. Tree rings from all over the world confirm it. That year, and for years after, trees almost stopped growing. The rings are incredibly narrow. They're rings of starvation. Now you take that physical evidence and put it next to the historical record, and what you see is chilling. Texts from across Eurasia talk about a strange, persistent gloom. A Byzantine historian wrote that the sun shone with no more strength than the moon. Frosts ruined crops in the middle of summer. Snow fell where it never had. Famine followed, and after the famine, with populations weakened, disease found an easy path. The Great Justinian plague swept through the Mediterranean starting in 541. It was a catastrophe that reshaped empires. It drained the strength of Byzantium and fed widespread unrest. That's the power of this ice core record. It doesn't just note a disaster, it connects dots across the planet. One violent event, captured in a chemical spike frozen at both poles, becomes the trigger for a cascade of human suffering. It shows how a civilization can be resilient to many slow pressures, but incredibly vulnerable to one sharp, global shock. The question isn't just about survival. It's about social cohesion. How does a kingdom, a culture, a people hold together when the sun itself seems to betray them? When the very rhythm of the seasons, the foundation of all agriculture, all planning, all faith just stops? The ice suggests that for some, the answer was that they could not. The volcanic signature is a knockout blow, preserved in acid, waiting in the ice for us to understand its terrible, unifying message. The wind moves through stone ruins on a Greenland shore. A Viking church still stands there. It was built by settlers who lived in that place for centuries. Their story is in the frozen record. The Norse came during a warm period around the year 1000. They found green land, they built farms, raised cattle, and their society lasted nearly 500 years. Then they were gone. For a long time it was a mystery. Did they leave? Was there a conflict? The ice cores from Greenland hold the environmental record. And that record tells a story of a world turning against them. The data shows a gradual shift. As the Little Ice Age began in the 13th century, the ice layers show a steady drop in temperature. It wasn't sudden, it was a creeping chill decade after decade. Summers got shorter and cooler. The growing season, already precarious that far north, shrank beyond what their farming could handle. Grass for livestock grew poorly, hay harvests failed. The core tells this through isotopes, a slow decline written in ice, but temperature was only part of it. The ice also holds evidence for sea ice. Tiny fragments and chemical signals show when the ocean froze earlier and thawed later. The records show these frozen seasons getting much longer. This had two devastating effects. First, it isolated them. The sea was their highway back to Iceland and Norway for trade and supplies. With the seas choked with ice for more of the year, that lifeline was cut. They were stranded. Second, the expanding sea ice changed the ecosystem. It likely disrupted the seals and walruses they hunted, making a crucial food source more unreliable. And here, the ice core data sets up a contrast. As the Norse struggled, another people thrived in the same landscape. The Inuit had arrived around the same time. Their technology was built for flexibility and mobility. They hunted seals on the winter ice, they fished, they adapted to what the environment provided. The Norse, though, clung to their identity as Scandinavian farmers. They were trying to replicate a European pastoral life in a climate turning hostile. Their social structure, their economy, their sense of themselves was tied to the land and their livestock. The ice doesn't record the final decisions, but it provides the backdrop, a backdrop of longer winters, shorter growing seasons, and impassable seas. The combination of that mounting climatic pressure and a deep cultural inflexibility seems to have been fatal. Farms were abandoned one by one. The last written record is from a wedding in the early 14th century. After that, silence and stones. This case is the perfect illustration. The ice core doesn't give a simple answer like a volcano. Instead, it gives the slow, accumulating pressure. It shows how a civilization can be perfectly suited to the world as it was, but vulnerable to the world as it became. The ruins are not just a mystery. They are a lesson in change and adaptation, written in the cold, clear layers of a glacier that watched it happen. That global climate signal recorded in ice, it also appears deep inside a tropical jungle. The Maya collapse is one of history's great puzzles, a civilization of huge intellectual and architectural achievement. Its great cities were abandoned to the forest in a very short time. Theories for a long time pointed to warfare or social revolt, but the answer wasn't in ice from their own region. It was in the connected climate system that ice cores help us see. There are no glaciers in the Yucatan, but the climate patterns that shaped the Maya world left their mark somewhere else. In ice cores from high mountain glaciers in the Andes, scientists see a pattern. Shifts in monsoon intensity, shifts in ocean temperatures that affect rainfall across the Americas. Those cores gave the framework. The local proof came from a different kind of archive. One that grew from the ceiling of a cave, stalagmites. In Yucatan caves, water drips from the ceiling, depositing minerals layer by layer over centuries. The chemistry of each layer is sensitive to how much rain fell above. In a wet year, the layer looks one way. In a dry year, it looks different. By analyzing these, scientists built a rainfall record with almost yearly precision. And what they found was a stark warning repeated. During the 9th and 10th centuries, the Maya heartland was hit by a series of severe droughts, multi-decade droughts. These weren't brief dry spells, they were profound shifts lasting a generation or more. The data shows rainfall dropping by up to half of normal levels for decades at a time. This climatic shift, seen in the Andean ice and detailed in the cave stones, lines up with the archaeological timeline of collapse. One by one, the great city-states fell silent. Tikal, Kapan, Palenque, their story isn't one single catastrophic event. It's a slow, grinding pressure that broke a complex system. The Maya were master hydrologists. They built vast reservoirs, intricate canal systems to capture rainwater for the long dry season. But these systems were designed for a certain range of climate. The prolonged droughts of the 9th century pushed them past their limit. The reservoirs dried up. The agricultural base that supported dense urban populations failed. You can picture the chain reaction. As water and food grew scarce, the social contract frayed. Maya kings derived their divine authority from their perceived ability to communicate with the gods, to ensure rain and good harvests. When the rains failed for years, that authority crumbled. Trust in the ruling order evaporated, like the water in the reservoirs. This led to political fragmentation. Conflict between cities competing for dwindling resources. People didn't vanish, they dispersed. They left the grand ceremonial centers, moved to smaller, more sustainable settlements, or to areas with more reliable water. The great civilization, as a centralized political force, unraveled under the unrelenting sun. This case shows the reach of ice core science. How these frozen records from distant mountains provide the key to hemispheric climate patterns. Patterns that, combined with local archives like cave formations, can solve a mystery thousands of miles away. The lesson from the Maya isn't simply about drought. It's about the vulnerability of even advanced societies when their most critical resource, the one their entire identity and infrastructure is built on, becomes unpredictable. The ice told us about the shift, the caves told us about the suffering. Together they rewrite the story of a fall, a sobering chronology of climate and consequence. Another story was unfolding far to the east, the Indus Valley civilization. It was a marvel, really flourishing over 4,000 years ago in what's now Pakistan and northwest India. Their cities, Harappa and Mohenjo-Daro, were masterpieces, grid-like streets, advanced drainage, a writing system we still can't read. Then, around 1900 BC, the lights in those cities began to dim. Their urban character just faded. For a long time, it was a mystery, no signs of invasion, no great fires. It seemed like they just chose to walk away. The answer, again, is in the dust, this time dust carried by the monsoon. The summer monsoon was their lifeblood. It filled the rivers, soaked the fields. When it failed, everything failed. To trace it, scientists looked to the Tibetan Plateau, the high Himalayas. Ice cores drilled their captured dust that tells a story of aridity. More dust in the layers means drier conditions down on the subcontinent. At the same time, there are sediment cores from the Arabian Sea, just south of the Indus. These ocean mud layers hold fossils of tiny marine creatures. Their chemistry is sensitive to the fresh water flowing from the rivers, water that came directly from the monsoon rains. These two distant archives together paint a clear picture, starting around 2200 BCE and deepening for centuries. The data shows a sustained weakening. The summer monsoon system was failing. The rains became less reliable, less intense. The great rivers, the Indus and the Ganga-Hakra, they began to shrink. This wasn't a sudden catastrophe. It was a slow squeeze, a climatic shift over generations. Think of a city built for abundance, granaries, public baths, all requiring vast amounts of water. Now imagine the wells running a little lower each year. The agricultural surplus that supported everyone, artisans, traders, administrators, it began to dwindle. The social complexity of urban life became harder to sustain. So what did they do? The evidence suggests they didn't vanish. They adapted. Faced with this prolonged drying, the population began a gradual migration eastward toward the foothills and the Gangetic Plain, where rainfall was more reliable. The grand, centralized urban model gave way to smaller, rural settlements. The civilization didn't end in a dramatic collapse. It transformed. Its people dispersed, carrying their culture into a new chapter. The cities weren't destroyed. They were slowly, thoughtfully abandoned. This changes how we see disappearance. The ice and the sediment show us that sometimes a civilization doesn't fall. It flows, it changes course in response to the changing earth. The story of the Indus isn't one of failure. It's resilience in a different form. The silent streets of Mohenjo-Daro aren't a tomb. They're a testament to a difficult, deliberate choice. A choice to leave a place when the land could no longer support the dream. Sometimes the clues that matter most are the ones you can't see. There are these tiny, ancient air bubbles trapped in the ice, and inside them there's another story. It's written in a gas, methane, an invisible trace that tells a story about life, but on a planetary scale. Methane is part of the Earth's natural cycle. It comes from wetlands, from animals digesting their food, and for thousands of years it's also come from human agriculture. When people clear land for farming, for flooded rice fields, when they keep large herds of livestock, they produce more methane. That methane mixes into the atmosphere. And a tiny, tiny fraction of it gets trapped in the polar snow. So the global methane level, in a very real sense, becomes a rough gauge of human farming activity. More farming, more people, more methane. And when you look at the methane record from the ice cores, you see a generally rising trend over the last 2,000 years as civilization expanded. But then you see the dips. One of the most profound ones happens in the 14th century. A clear, sharp decline in global methane. This wasn't from a change in wetlands. It lines up with two of the most devastating events in recorded history. The Mongol invasions across Eurasia, which caused widespread disruption and loss. And the arrival of the Black Death, the pandemic that swept across continents. The scale of the population change in that century is almost beyond comprehension. Estimates suggest the global human population may have fallen by as much as a quarter. Vast areas of farmland were abandoned, fields returned to forest. Herds dwindled. The global human footprint on the planet for a brief, terrible period actually shrank, and the atmosphere recorded it. That dip in methane is the chemical signature of that emptiness. A planetary scale biomarker for desolation. So what does a drop in a gas tell us? It forces a shift. We're used to thinking of history in terms of kings and battles, of art and architecture rising and falling. But this evidence asks us to think in terms of biology and chemistry. It shows human civilization not just as a cultural phenomenon, but as a geological force. Our numbers, our farming, our very presence changes the composition of the air itself, and when our numbers crash, the planet breathes a different sigh. It's a hauntingly impersonal record. The ice doesn't record the individual stories of that century, the personal loss, the fear, the collapse of communities. It records the silent, integrated aftermath, the fields gone quiet, the global drop in a gas. This clue offers a view of civilizational upheaval from the highest possible vantage point. It's not about one society vanishing, but about a sudden, violent contraction of the human project itself. The methane dip is a reminder that our history is tied to the Earth systems. Our expansions and our contractions leave a mark in the very air, preserved in ice for a future generation to find. It turns a question about vanished cities into a question about the rhythm of life on a global scale. And it sets the stage for the most pressing question of all, the one that brings this frozen history into our own time. The volcanic acid in the ice isn't just about global winters. There's one signature that points to a blast that reshaped a whole sea. On Crete, there was this brilliant civilization, the Minoans. They built these labyrinthine palaces with frescoes of dolphins and athletes. Their ships dominated the eastern Mediterranean, this whole web of trade. Their society seemed secure, vibrant, advanced. Then the mountain in the sea woke up. Thera, north of Crete, exploded. One of the most violent eruptions in human history. We know the precise scale not from Minoan records, but from ice cores. From Greenland, in the layers around 1600 BC, there's a sulfate spike. Staggering. It matches a signal in Antarctic ice. This global bookmark confirms it was a cataclysm that touched the entire planet. The local effects were beyond imagination. The eruption would have been heard across continents. It generated tsunamis, walls of water radiating across the Aegean, crashing into Crete's northern coast. Harbors, coastal settlements, the lifeblood of a maritime empire, devastated in an instant. Then came the ash. A thick blanket fell across the region, smothering fields on Crete, poisoning the soil, collapsing roofs. The sky darkened for days, maybe weeks, but the immediate devastation was just the beginning. The material shot into the stratosphere triggered significant cooling. Tree rings from Ireland and California show stunted growth right then, evidence of several cold, poor growing seasons after the eruption. For the Minoans, this meant a cascade. Their agricultural base was damaged by ash, then challenged by the altered weather. Their fleet, their source of wealth, was crippled by lost ports and disrupted trade. The psychological impact would have been profound. How could their gods or their priest king at Knossos have allowed this? The ice core evidence is crucial here. It helps separate a real geological disaster from later myth. The story of Atlantis, an island kingdom that sank in a day and night, was recorded by Plato centuries later. Many see in that a distant, garbled memory of Thera and the decline of Minoan Crete. The sulfate spike in the ice gives that legend an anchor in measurable, physical reality. The Minoan civilization didn't vanish overnight in the ash. They persisted for maybe another century or two, but they were severely weakened, a wounded giant. Their influence waned. Into that vacuum moved the Mycenaeans from the Greek mainland, a more warlike culture. They eventually took control of Crete, absorbed what remained. The eruption wasn't a single knockout blow. It was a shattering shock, a deep wound this unique maritime culture never fully recovered from. The ice core, with its silent chemical scream from 1600 BC, marks the moment the world changed for the people of the labyrinth. It shows how a single, localized event recorded globally in ice can set in motion the slow unraveling of a world. The wind carries life, tiny things. Pollen spores, they travel for thousands of miles, and when they land on a glacier, they freeze. They're preserved. That's the fifth clue from the ice. A botanical record. To read it, you go microscopic. Scientists melt a piece of an ice core. They filter the water. They look at what's left under a microscope. And they find a hidden world, pollen from specific trees, spores from certain fungi, even tiny bits of charcoal from old fires. Each one is a data point. A message about the landscape it came from. A core from the Andes tells a story. In the early layers, the pollen is from native trees. It shows a stable, forested place. Then, as human societies grow, the signature changes. Tree pollen starts to decline, and in its place you see a rise, pollen from maize, from quinoa. From other crops, you see spores from fungi that like disturbed soil. That's the clear signal of agriculture, forests being cleared for fields. It's a record of a civilization shaping its world. Turning wilderness into farmland. For a time, the record shows a balance, but then, in some cores, it shifts again. The pollen from crops begins to fade. Spores from weeds, the kind that take over abandoned land, they increase. And then, crucially, you see a layer, a sudden spike in tiny charcoal particles. That sequence tells a story. First, the intensive farming. Then, maybe during a drought, the exposed soil begins to fail. Erosion sets in. The land can't support the people anymore. Fires sweep across the degraded landscape. Finally, the crop pollen vanishes. It's replaced by the pollen of weeds, reclaiming the empty fields. This evidence adds a layer. An ecological intimacy. It's not just about temperature or rainfall. It's about the plants under their feet. The ice shows the moment the relationship between a people and their land became strained. It shows the feedback loop. A society clears land to thrive, but that act makes the land more fragile, especially when the climate turns less forgiving. The pollen and spores are a ledger of that relationship, of prosperity and then of strain. By reading this microscopic writing, you see the environmental cost. You see how a civilization's success can plant the seeds of its own vulnerability. Long before any political crisis, the ice preserves not just the weather they endured, but the living landscape they helped create. And in some cases helped unravel. It's the most intimate clue, a ghostly garden suspended in ice. It tells us how deeply our fate is woven into the soil, the trees, and the wind that carries their essence. The wooden tablets of Easter Island, the Rongorongo script, it's still undeciphered, but there's another record on the other side of the world, in the West Antarctic ice sheets. Scientists drill down and they find a chemical record of the southern hemisphere's climate. Shifts in atmospheric pressure, changes in sea ice, all of it leaves a mark. And that data shows something. It shows long periods of intensified drought across the Pacific region. These were hemispheric shifts, not local. These were climate patterns that would have redirected rain away from that island. For years, for decades now, the island itself, Rapa Nui, a small, isolated triangle of land, its ecosystem was fragile. the common story of its collapse talks about the statues, the trees. Ecological overuse, but this ice core data adds a layer. It suggests the people there weren't in a stable climate. The stage was tilting beneath them. The evidence points to significant droughts, particularly between the 13th and 15th centuries, which is right during the peak of statue construction. The peak of societal complexity. A drought there, it isn't just a water shortage. On an island with limited resources, it means less water for the sweet potato crops. It stresses the few remaining palm trees. It dries the soil, making it vulnerable to erosion when the rain finally comes. This environmental pressure, written in distant ice, would have intensified every challenge. Moving those great Moai statues required immense coordination, surplus labor. In good times, that was an expression of faith and power, but during extended dry periods, that same effort could become a source of strain. Competition for dwindling resources, fertile land, fresh water, that would have fueled tensions between clans. The ice doesn't tell us about specific conflicts, but it provides the harsh, dry backdrop, the backdrop against which social bonds would have been tested. So the Rongorongo script is silent, but the Antarctic ice speaks. It moves the narrative beyond a simple story of a people using up their environment. It presents something more complex, a society of incredible ingenuity, building a unique culture in profound isolation. Then faced with a changing climate they couldn't have foreseen, their adaptive systems were pushed beyond a breaking point. The decisions they made to keep carving statues, how to allocate scarce food, how to deal with neighboring groups, all those decisions were made under a deepening environmental shadow. The ice core gives us that shadow. It turns the mystery of the fallen statues into a lesson about resilience under remote and mounting pressure. A story written not in wood, but in the frozen breath of the entire Southern Ocean. Sea salt frozen in the ice, it's the taste of the ocean captured. When you look at an ice core, you measure sodium ions. They come from sea spray, from wind and waves. More salt in a layer means stronger winds that year, more storms, a more turbulent ocean. It's a direct log of the sea's mood, and for societies tied to the ocean, this record shows rising danger. Take the Norse in Greenland again. We already saw colder temperatures, longer sea ice choking their routes. The sodium layers add something. In the centuries before their silence, ice cores from there show more variability in the salt. Spikes, periods of intense storminess. Picture the North Atlantic in a fury. The routes they needed to Iceland for trade, for iron and timber became lethal. A voyage that was a calculated risk turned into a near-suicidal gamble. That didn't just cut them off physically, it isolated them culturally, psychologically. Severed the thread to their Scandinavian identity. The ocean was their highway, it became a wall. This clue goes farther. Think of the Polynesians, navigating the open Pacific by stars and waves. Their whole civilization was mastering the sea. Periods of increased storminess recorded in ice from Antarctica and high glaciers would have been a profound challenge. More storms make celestial navigation harder. They raise the risk of catastrophic loss on long voyages. They could disrupt the whole web connecting island communities. A sustained period of rougher seas, a salty band in the ice, might not end exploration, but it could contract it, make societies more insular, more focused on survival than expansion. More vulnerable to local pressures. The salt isn't just about danger, it's about predictability. Maritime cultures build their rhythms around known patterns of wind and weather. When those patterns turn erratic, when calm seasons break with violent gales, it undermines the knowledge built over generations. The elder who knew when to sail finds his wisdom obsolete. The ocean becomes a stranger. This shifts the perspective. We think of climate change as heat or cold, rain or drought, but the sodium ions tell us it's also about energy. The energy in the wind, in the waves. A change in that energy reshapes the distances between people. It can turn a highway into a barrier, a source of abundance into a source of peril. For a society built on mastering the sea, a shift in its fundamental temperament isn't an environmental footnote. It's an existential challenge. The frozen spray in the ice is the ghost of those tempests. A silent record of the day the waves began telling a different, more forbidding story. Mesopotamia. That name means the land between the rivers. It was the cradle of civilization. And it was the first to show how fragile that cradle could be. Sargon of Akkad built the world's first true empire there around 2300 BC. He united the rival city-states of Sumer. His rule stretched from the Persian Gulf to the Mediterranean. It was an unprecedented achievement: administration, culture, military power. But then, within just 200 years, that empire shattered. Its grand cities were abandoned. Its written records fall silent. For a long time, scholars thought it was rebellion or invasion. But the real story was written in dust, and that dust fell on ice thousands of miles away, on Mount Kilimanjaro in Africa and in the glaciers of the Alps. Ice cores hold a record. In the layers from around 2200 BC, there's a dramatic spike. A spike in dust, fine, wind-blown particles. This dust didn't come from nearby. Its chemical fingerprint points to a vast, arid region. The analysis points to the Middle East, to the drying soils of the Fertile Crescent itself. That's the signature of the 4.2 kiloyear event. A global shift to a drier climate that lasted for centuries. The ice cores capture its onset. For Mesopotamia, this meant the rains failed. The Tigris and Euphrates, their flows diminished. The intricate irrigation canals began to choke with silt. The agricultural surplus that fed the cities, that paid the soldiers, it began to vanish. You can see the evidence on the ground. At Tel Leilan in modern Syria, it was a major Akkadian center. Researchers found a layer of sterile, wind-blown dirt there. No pottery, no artifacts. Just dust. It sits right on top of the Akkadian ruins from exactly this period. The land literally blew away. What followed was a chain reaction. Crop failures led to food shortages. Famine weakened the population. Central authority, which depended on ensuring prosperity, lost its legitimacy. The social contract frayed. In desperation, people abandoned the great urban centers. They dispersed into smaller, more mobile groups, and into this power vacuum came new pressures, nomadic pastoralist groups from the northern fringes. Like the Guetians, described later as relentless, they were likely fleeing the same drought, searching for land for their herds. To the weakened Akkadian cities, these incursions were the final blow. The empire didn't fall in a single battle. It disintegrated. It fragmented back into struggling, isolated city-states. Sargon's unifying vision evaporated under the unrelenting sun, under the constant, dust-laden wind. This is where the ice core evidence changes things. It takes a historical mystery, a footnote about an empire's end, and turns it into one of the earliest cases of climate-induced collapse. The dust in that ice isn't just sediment. It's the physical evidence of the drought that broke the world's first experiment in empire. It shows that even at the dawn of complex civilization, human ambition was tethered to the climate. A shift in the wind, a change in the rain could erase the grandest political designs. The story of Akkad is a foundational lesson, a lesson written not only on clay tablets, but in the dust of its own demise. Carried by the wind and sealed in ice a continent away, fire leaves a ghost, a dark fingerprint in the ice. You melt a section of an ice core, filter the water, and you see it. Tiny particles, black carbon, pure soot, these are the final remains of a flame from centuries ago, carried by the wind for thousands of miles before settling on a glacier. That's the seventh clue, a record of ancient fires written in darkness. Some fires are natural, lightning in a dry forest, but the patterns tell a deeper story. A steady, widespread increase in black carbon over many years. That isn't random wildfire, it's a signal. It points to systematic human activity, to land clearing on a massive scale, to slash and burn agriculture, opening new frontiers for farming empires. Picture a dynasty at its peak in ancient China. Population growing, the demand for farmland pushes people into new territories. They set fires to clear forests to create fertile ash for crops. Year after year, that smoke rises. It joins the atmosphere, and a fraction of it journeys to the highest, coldest places on Earth. In ice cores from the Tibetan Plateau, scientists see these patterns, long, rising trends of black carbon. They correspond with periods of agricultural expansion under powerful dynasties, like the Han or the Tang. The ice holds the soot of their growth, the atmospheric cost of their prosperity, but then the record can turn. A sustained increase is followed by something just as telling. A sharp, sudden drop, a plunge in the soot layers. That isn't the story of cleaner technology. It's the story of collapse, land abandonment. When political order fragments, when populations crash from conflict or illness, when central authority can no longer protect its frontiers, those farmlands at the edge are the first to go. The fields return to wild grasses, the fires stop, the constant stream of smoke into the sky ceases, and the ice far away records the new silence. The absence of soot becomes a proxy for the absence of people, for the retreat of civilization from a landscape it once tried to tame. This clue adds something to the environmental portfolio. It shows our interaction with fire, one of humanity's oldest tools, wasn't just local. It was a planetary-scale phenomenon, even in antiquity. The act of clearing a forest to plant wheat in the Yellow River Valley left a chemical trace in a Tibetan glacier. It connects human ambition directly to the Earth's atmospheric chemistry, and it shows that our retreats, our collapses, are also recorded, not just in silent cities, but in the sudden cleansing of the air. The story isn't just about temperature or drought. It's about the very air we filled with the evidence of our presence, and the stark clarity that followed when that presence faded. The black carbon layers are a chronicle of flame and ambition, of growth and its eventual smoky end. The stones of Angkor Wat tell one story, but the empire that built it faced something else. The Khmer Empire depended on the monsoon. Its whole project was a prayer for water. They answered it with a network, canals, reservoirs, these massive artificial lakes called barrays. They turned the landscape into a managed watershed. That system was their masterpiece. It let them support a huge population, build these wonders, but then the rain's rhythm changed. And you see that answer far from the temples, in caves, ice, speleothems, these cave formations from nearby regions. They're like ancient rain gauges. Their chemical layers show the monsoon's strength over centuries, and for the Khmer, it's a troubling story. In the 14th and 15th centuries, the pattern broke. The reliable monsoon turned fickle. The data shows sharp swings, long, severe droughts, then periods of intense, catastrophic flooding. This wasn't just a shift. It was a volatility the system couldn't handle. A massive reservoir is brilliant for storing seasonal rain, but it's helpless against a drought that lasts for years, slowly evaporating its reserves. And those same engineered canals could be shattered by a sudden deluge, silted up, rendered useless. The environmental stress was a constant, grinding pressure. This climatic picture, supported by ice core records, lines up with a pivotal time for the empire. Historical evidence shows political fragmentation. A religious shift from the god-king cult of Hinduism toward the more egalitarian Theravada Buddhism. It's too simple to say the drought caused the change. But it's compelling. A prolonged environmental crisis could undermine the very foundation of royal authority. If the king, seen as a divine conduit, could no longer ensure the rains and the harvests, his power would wane. The grand capital of Ankara, with its massive infrastructure, may have just become too difficult to sustain. The population likely began a gradual drift toward the Mekong Delta, other areas with more reliable water. Following the resource security the Central Plains couldn't guarantee anymore, Ankara wasn't sacked. It wasn't suddenly abandoned. Its story is a gradual loss of centrality, a slow fading as the environment it was engineered for transformed into something new, something unmanageable. It's a lesson in scale. A civilization can build monuments to outlast the ages and still find itself vulnerable to a subtle, persistent change in the wind. In the rain, the water molecules trapped in ice, they hold a memory of the ancient air. Inside each frozen crystal, you have two kinds of oxygen atoms and two kinds of hydrogen. Most are common, but a tiny fraction are heavier. They carry extra neutrons. These are stable isotopes, and their behavior is the key. When ocean water evaporates, the lighter, more common molecules evaporate a little more easily. As that moist air moves toward the poles and cools, the heavier molecules, with their extra weight, they tend to fall out first as rain or snow. So by the time a snowflake forms over Greenland or Antarctica, its isotopic composition tells a story. It tells how far it traveled and how cold that journey was. In a warm period, there's more energy in the system. The heavier isotopes travel farther, all the way to the poles before they fall. The snow that accumulates there in a warm era has a higher proportion of those heavy isotopes. In a cold period with less atmospheric energy, the heavy isotopes fall out much sooner. The polar snow becomes depleted of them. It becomes lighter isotopically. This difference is minuscule, but it's measurable with incredible precision. By drilling down through an ice core and measuring the oxygen 18 to oxygen 16 ratio in each layer, scientists don't just see annual changes. They build a continuous, high-resolution thermometer, a thermometer that stretches back 800,000 years in the oldest Antarctic cores. This isotopic record is the foundational rhythm track of paleoclimatology. It's the baseline tempo of the planet's climate. Every other clue, the dust, the volcanic acids, the greenhouse gases, is layered over this fundamental temperature score. It lets us ask the critical contextual questions. Did the Akkadian Empire collapse during a long, deep, cold snap? The isotopes show a sudden, severe shift toward aridity, but one that was embedded in a broader cooling trend. Did the Norse arrive in Greenland during a warm period? Absolutely. The isotopes from Greenland ice show a clear medieval warm peak, a window of opportunity that later slammed shut with the Little Ice Age cooling. The story of the Maya unfolds against a backdrop of a more variable, unstable climate, with droughts hitting during what was already a naturally drier period in the region's cycle. Without this isotopic timeline, the other clues would be isolated events. With it, they become part of a pattern. We can tell a local drought from a global chill. We can see if a volcanic winter was an extra blow during an already difficult cooling phase, or a shock to a stable, warm system. This data transforms history. It turns it from a series of isolated human dramas into a dialogue, a long, intricate dialogue between human societies and the planetary climate system. The isotopes in the ice give us the planet's side of that conversation, a conversation about temperature, written in the frozen language of ancient water. One snowflake at a time, the Tang dynasty was a golden age. Poetry, painting, trade, all of it flourished. China was connected to the world. Its capital, Chang'an, was a global city. And the Silk Road was its lifeline. That's what brought wealth, ideas, prestige from Central Asia and beyond. For centuries, it seemed unshakable. Then, in the 9th century, things began to fray. Rebellions started, the central government's control weakened, the empire fragmented slowly. Historians have studied the political reasons, the military reasons. But the ice from the Tibetan Plateau tells another story, a story of dust and distance. Up on the Gulia ice cap, scientists found a clear signal. In the layers from the 8th and 9th centuries, there's a dramatic increase in dust. Fine, wind-blown particles. That dust came from the arid heart of Central Asia. Its chemical signature points to a prolonged drought, a severe one. The grasslands of the steppe, the very corridors that made the Silk Road possible, were turning to dust. That shift had immediate consequences. For the nomadic tribes living on those grasslands, their traditional way of life was threatened. Pastures failed. Water sources dried up, their herds suffered. Faced with that pressure, these mobile, skilled horsemen often looked south and east, toward the settled, wealthy lands. The Tang Empire's borders became a pressure point. Incursions increased. The empire had to divert massive resources to fortify its frontiers. That strained its military. It strained its treasury. At the same time, the Silk Road itself became more perilous, less profitable. Oasis towns that depended on passing caravans struggled. Trade volumes probably dropped. The economic vitality that helped sustain the Tang's cosmopolitan culture began to ebb, and there's another layer in the ice. From the same period, ice cores from both poles show evidence of major volcanic eruptions. One big event, likely in the year 836, left a clear sulfate spike. An eruption like that would have pumped sun-blocking aerosols into the stratosphere. That leads to regional cooling. Historical records from China and Korea mention unseasonable cold. Summer frosts, widespread crop failures around that time. So imagine the strain. A distant drought pressures the borders and trade routes. Then a volcanic winter triggers famine in the agricultural heartland. The central government, already dealing with rebellious military governors, now faced a crisis of subsistence, a crisis of legitimacy. Could it feed its people? Could it protect them? The answer, increasingly, was no. This sequence shows the interconnectedness of the ancient world. A drought on the Central Asian steppe, recorded in Tibetan ice, could shake an empire in Chang'an. A volcano erupting somewhere else on the planet could deepen its crisis. The Tang dynasty's twilight wasn't caused by climate alone, but the ice core evidence reveals the environmental stage. The stage where its political drama played out. It shows how a globalized empire, for all its cultural and military might, remained tied to the climate of regions far beyond its control. The dust in the ice is a silent testament to that vulnerability, a reminder that even the most glorious golden ages are conducted in dialogue with the earth. Inside the ice, there's a kind of periodic table of what people tried to do. You have the lead, the copper, but then there are other metals, zinc, cadmium. Antimony, you can't see them, but they're there, and each one points to a specific craft. Zinc and copper together, that might mean brass was being made. A lot of antimony, that could be glassmaking, ceramics. These aren't just pollution, they're echoes. Each new technique, each material people learned to use, left a fingerprint in the air. And when that fingerprint disappears from the ice, it means something. It means that knowledge was forgotten. Think about the Romans. They mined lead for silver. But their work was so precise, it left a specific mark. The lead from Spanish mines has a different atomic signature than lead from British mines. So when scientists look at lead in Greenland ice, they can sometimes trace it. Not just to Rome, but to the exact province where it was mined. It's a tag, a chemical tag on a transaction 2,000 years old, carried by the wind and kept in the ice. That turns the ice into a ledger, a record of technological skill. A steady rise in certain metals means a society was refining its crafts, expanding what it could make. But the record isn't a straight line going up, it's peaks and troughs. There's a sharp peak of zinc during China's Song dynasty. Their metallurgy was advanced. Then a decline, a trough. Dynasties changed, conflict happened, those networks of skill broke apart. The knowledge of how to make a certain alloy, how to smelt a particular ore, it might not have been lost completely. But the practice of it, the widespread industrial use, could stop for generations. The ice records those pauses, those periods of going backward. It shows that progress isn't inevitable. It isn't a one-way street. It's fragile. It needs stability. It needs masters teaching apprentices. It needs trade routes for materials. It needs a society with enough wealth to experiment. When those conditions fall apart, the graph falls. The intricate knowledge to make a certain steel or a vivid glaze goes dormant. It might survive in a few texts or in broken artifacts we dig up later. But its active pulse, its measurable output into the air stops, and the ice core year by year notes the silence. So these trace metals tell a subtler history. Not of empires and kings, but of workshops, of forges, of the quiet, cumulative genius of artisans. Their collective breath, carrying the dust of their craft, became part of the planet's record. And their silence, when it came, became part of that record too, a frozen testament. Our technological heights aren't permanent summits. They're camps we make on a mountainside. Always vulnerable to the weather, the next layer in the ice holds a different whisper, not about industry, about life and its abrupt planet-wide transitions. Across the Mississippi, from where St. Louis is now, there was a city, Cahokia. It was the biggest settlement north of Mexico before Columbus. Around 1100 at its height, maybe 20,000 people lived there. They built huge mounds of earth. The biggest one was 100 feet tall. It was a center for ceremony, for trade, for power, a complex society with connections that stretched far. Then, by the 1400s, the city was mostly empty. The mounds were just there, silent. The question is why. There aren't any glaciers in Illinois. No ice cores from the Midwest, but the climate that affected Cahokia left its mark somewhere else, in the frozen records from Greenland and the Arctic. The climate patterns for the whole hemisphere recorded there show a world becoming more variable, more extreme, and that story reached all the way to the American heartland. Reconstructions from those distant ice cores point to a time of big climate shifts. During the centuries, Cahokia rose and fell. The data shows periods of serious drought across the northern hemisphere. It also shows times of unusual cold, tied to volcanic eruptions or other global forces. For a society built on maize on the fertile floodplains of the Mississippi, these weren't abstract changes. A long drought would have stressed the crops that fed the city. A string of cold summers could have shortened the growing season, cutting the harvest. The environmental base of Cahokia's wealth and population was under pressure. Then there's the archaeological evidence from the site itself. Scientists took soil cores from under Cahokia's mounds. They found signs of catastrophic flooding, layers of silt and sand left behind when the Mississippi overflowed its banks. Think about that impact. Floods could wipe out a season's planting, destroy stored food, contaminate the fresh water. A city on a floodplain has a relationship with the river. It depends on the river's seasonal deposits for good soil. But if the river's behavior gets more erratic, swinging from drought to flood, that relationship becomes dangerous. So the picture that comes together is one of growing environmental stress. The broad hemispheric instability from the ice cores sets the stage. Then local events like major floods deliver the sharp blows. For the people of Cahokia, this probably meant food insecurity. It meant hardship. When a centralized society can't reliably provide for its people, the social bonds start to fray. The authority of the leaders, who might have been seen as intermediaries with the forces that control rain and river, would be challenged. The dispersal of Cahokia's population looks like a gradual process, not one single catastrophe. People likely moved out to smaller, more sustainable communities. They may have gone back to a more decentralized way of life, less urban, one that was more resilient to an unpredictable climate. The great city wasn't conquered. It wasn't destroyed. It was slowly, it seems thoughtfully, depopulated. Its people adapted by changing their relationship with the land and with each other. And this is where the ice core data gives that deeper context. It shows Cahokia's story wasn't an isolated mystery. It was part of a larger pattern, climatic change affecting societies across the globe in that period. The same broad forces that brought drought to the Maya or cold summers to the Norse in Greenland were also at work in different ways along the Mississippi. The silent mounds of Cahokia aren't just an American enigma. They're a local expression of a global climatic chapter, a chapter whose opening lines are written in ice a continent away. The city's fate is a reminder. Even the most impressive human achievements are a conversation with a dynamic planet. The ice tells us what happened and how fast it happened. That's the 10th clue, the speed. Sometimes the most surprising thing in the cores isn't a new state, but how quickly the old one disappeared. You can read the layers in such fine detail. You can see winter snow and summer snow from the same year. And that detail shows moments when the climate didn't drift. It flipped like a switch. Within a generation, sometimes less, the rules changed completely. For a society that depends on predictable seasons, a shift that fast isn't something you adapt to. It's the floor falling out. That idea is called abrupt climate change. And the ice shows it happening over and over. One of the clearest examples is way down in the oldest ice. About 12,000 years ago, the Earth was warming up, coming out of the Ice Age. Then it reversed suddenly. Temperatures in the North Atlantic dropped. That period is called the Younger Dryas. Glacial conditions came back for more than 1,000 years. The ice core data says that transition started in decades, not centuries, decades. The isotopic signal drops, dust levels jump, meaning it got dry and windy. For the people living then, the world must have felt broken. A summer that never got warm, a harvest that failed year after year. For hunter-gatherers, the whole map of survival where animals went, what plants grew would have been scrambled almost overnight. There was no time for new tools, new ways of living. The only choice was to move, to follow a climate that was moving faster than they could. This clue changes how we see historical vulnerability. A civilization might handle a slow drought over a century. It can adjust its farming, its water. But what if the drought arrives in full in 20 years? What if the monsoon just stops within one person's lifetime? The ice suggests that for some of these past societies, the problem wasn't just the change. It was the rate. A sudden volcanic winter, a drought that intensified fast. These things didn't allow for slow adaptation. They required an emergency response. And large, complex societies with their fixed infrastructure and deep hierarchies are usually the worst at emergency response. They're built for stability, not for quick reinvention. The lesson in these high-resolution layers is sobering. Resilience isn't just how much change you can take. It's how fast you can see it and turn. The frozen record tells us the planet's history has these sudden jumps. Moments when the stage of human history was pulled away and a new, strange one shoved into place. For the people in that transition, it must have felt like the end of the world. And for their world, it was. That frozen library isn't just data. There's a deep irony there. The Maya watched the stars with such precision. The Norse used them to sail open seas. But none of them could see the story being written in the ice caps a world away. They were master chroniclers of their own skies, yet the planetary climate was this invisible author, writing their fate in silence. So the Ice Core Archive is like a volume recovered from the Library of Alexandria, a volume those civilizations never knew was there. The burning of the Great Library was a human tragedy. Lost texts on engineering, philosophy, medicine, but a civilization's collapse is a deeper kind of loss. When the Indus Valley's center faded, their urban planning, their standardized weights, it all became obscure. When the last Norse settler left Greenland, the knowledge of farming that far north, the adaptations to that brief warm period, it just dissipated. These were libraries of lived experience. libraries of environmental adaptation, and they were lost when the communities that held them dispersed or ceased. Now the ice cores let us read a foundational text those cultures couldn't access. The environmental conditions they lived within. We can see the drought that stressed the Maya reservoirs. We can measure the creeping cold that shortened the Norse growing season. This is the missing chapter. It helps us understand not just that they fell, but why their solutions, brilliant for their time, hit a limit. Their cultural memory, their toolkit, it was built for the climate they knew. When the climate changed beyond the range of their experience, their library of solutions had no reference for the new reality. So we're in a unique position. We're using one library written in ice to understand the gaps in the lost human libraries of the past. We're piecing together the full narrative of their challenges. This isn't about blame, it's about comprehending the complete set of pressures they faced. The ice record gives us the context they lacked, the long-term planetary rhythms they could not perceive. It turns their collapses from mysterious failures into understandable human stories. Stories set against a shifting, powerful natural world, and in doing that, it asks us a quiet question. An urgent one about our own vast library of knowledge and what unseen forces it might be missing. A volcano's explosion leaves a signature, not just in acid. In glass, microscopic shards of volcanic glass tephra get blasted high into the atmosphere. Every volcano has a distinct chemical fingerprint in its magma. The tephra it produces carries that same fingerprint, and when these tiny glass particles land on a glacier, they get sealed in place. They wait. For a scientist reading an ice core, finding a layer of tephra is like finding a name tag. It tells you exactly which volcano erupted and when. That's the 11th clue. It turns a generic sulfate spike, just a sign of some distant cataclysm, into a specific, named historical event. You move from a question to an answer, from wondering what caused a dark year in the record to knowing. Take 1257. Ice cores from Greenland and Antarctica show a colossal sulfate spike. One of the largest in 2,000 years. For a long time, it was an anonymous climate event. Then researchers found the tephra, tiny glass shards in that same ice layer. They analyzed the chemical composition. It was a perfect match. The source wasn't Iceland or Italy, as some had guessed. It was Mount Samalas on the island of Lombok in Indonesia. A volcano halfway around the world. The eruption was cataclysmic, likely one of the most powerful of the last millennium. Now, with that name and date secured, historians could look at the human record with new clarity. European chronicles from the years that followed describe a period they called the years without a summer. Unseasonable cold, relentless rain, crop failures, famine. The tephra in the ice provided the missing link. It was the Samalas eruption that pumped so much sulfur into the stratosphere, cooling the planet and triggering that wave of hardship. A mystery of cause and effect, solved by particles of glass smaller than a grain of sand. This precision changes how you see the chain. It lets you map the fallout of a single explosion across the globe. You can trace its ash cloud in the atmosphere, its cooling effect in tree rings, its social consequences in written accounts of hunger and displacement. The tephra turns a climate signal into a historical bookmark. It lets you say with certainty that this volcano on this date contributed to that crisis. It brings the story into sharp focus, a heartbreaking focus. You're no longer dealing with abstract forces. You're witnessing the precise moment when a mountain on a tropical island altered the fate of farmers in England, villagers in France. The glass shards are the ultimate corroborating witness, silent, immutable, perfectly specific. They remind you that in the grand narrative of human and planetary history, sometimes the most crucial details are the smallest ones. Those glass shards give us a precise record, a record of the past, but you could turn that around. You could look at the most recent layers of that frozen archive not as history, but as a message. A message for us: the ice cores showed us the stage for past collapses. Now they hold up a mirror to our moment, and what's reflected there, it's nothing like the rest of the archive. For 800,000 years, carbon dioxide in the air had a rhythm, a predictable cycle. It moved between about 180 and 300 parts per million, in sync with the ice ages. You see this gentle wave in the tiny air bubbles, methane too. These were the planet's natural breaths, in and out over vast time. The changes were gradual. Thousands of years, even the sharp volcanic spikes, the droughts that hit ancient societies, they happened inside that slow, larger heartbeat. Then you look at the very top. The last 2 centuries, the line doesn't curve, it shoots up, a vertical climb. Carbon dioxide went from about 280 parts per million before industry to over 420 now. That's a shift bigger than the entire natural swing between an ice age and a warm period. But the critical difference is the rate. In the past, that full swing took 5–10,000 years. We've done the same in just over 200. The speed of change isn't just faster, it's off the charts of the ice core record. Methane tells the same story. A steep, relentless climb from human activity, agriculture, fossil fuels. The graph doesn't look like a natural process, it looks like the reading of an explosion. That's the core of the warning. The societies we talked about, the Maya, the Akkadians, the Norse, they faced big climate challenges, but those challenges unfolded over decades, generations. They had time, however hard, to adapt, to move, to try things. Their world changed faster than they could handle sometimes, but it was still within the planet's known variability. Our situation is different, categorically. We're not passengers on a planet having a natural shift. We are the engine, driving a change that has no precedent in the 800,000-year archive. The force and speed of what we're doing to the atmosphere, it dwarfs the natural variations that unraveled past civilizations. So the reflective question is urgent. If slower, natural climate shifts tested empires and contributed to their fall, what does that imply for us? For a global civilization facing a change of greater magnitude at a breathtaking speed. The ice core record suggests the main threat may not be the change itself, but the rate. It's the velocity of the transformation. That's what outstrips the capacity to adapt our agriculture, water systems, coastal cities, international stability. This frozen library isn't just an archaeological tool, it's a baseline, a control experiment written in ice. It shows the boundaries of natural climate variability and how human societies fared inside them. Our current data point is far outside those historical boundaries. The lesson from the vanished isn't that climate change always destroys civilizations. It's that civilizations are deeply vulnerable to rapid environmental change, especially when their systems are inflexible and they don't fully understand the threat. We uniquely have the understanding. We've read the book. The final chapter, the one we're writing now in the air, is a question. It asks if a civilization that can decode warnings from ancient ice is wise enough to heed the warning written in the sky above it. The frozen library gives us a powerful voice, but it's not the only voice in the story. The ice core record is a silent witness. It speaks with precision about the what and the when. It tells us the year the rains failed, the decade the temperatures plunged, the century the lead pollution stopped. It provides the environmental stage with clarity. But it can't tell us the human drama that played out on that stage, the political decisions made in a smoky hall, the social tensions that fractured a community, the cultural beliefs that guided a people's choices. The ice shows us the pressure, but not how a society chose to bear it. Take the Greenland Norse again. The ice cores tell us about the creeping cold of the Little Ice Age, the longer sea ice seasons, the increasing storminess. That's the indispensable context. But the core can't tell us why the Norse clung to their identity as Scandinavian farmers. refusing to adopt the hunting technologies of the Inuit who thrived around them. That was a cultural choice. It can't tell us about the specific trade negotiations that failed, or the internal leadership disputes that may have paralyzed their response. Those were political and social factors. The disappearance wasn't caused by climate alone. It was the result of climate intersecting with a particular set of human decisions and values and vulnerabilities. This distinction is crucial. To see only the climatic data is to risk a kind of environmental determinism. It reduces the complex tapestry of history to a simple reaction to weather. The truth is more intricate. Two societies can face identical climatic stress and follow completely different paths. One may innovate, adapt its agriculture, and forge new trade alliances. Another may fracture into conflict, its institutions unable to manage the crisis. The ice core gives both societies the same climatic script, but their cultures, their leaders, their social structures, these are the actors who decide how the lines are delivered. And how the play ends. This is where the disciplines must join hands. The ice core scientist provides the hard environmental chronology. The archaeologist excavates the hearths and the tools and the seeds to see how daily life changed. The historian pores over any surviving texts for mentions of grain prices or royal edicts. Together, they build a complete narrative. The ice tells us there was a great drought in the 9th century Yucatan. The archaeology of the Maya cities shows us the reservoirs were abandoned and the palaces burned. The glyphs on the monuments hint at the wars between city-states that flared as resources grew scarce. One source gives us the condition, the others give us the consequence and the human action, so the frozen archive is not a verdict. It's a key witness providing evidence that was missing. It allows us to ask better questions. Instead of wondering why a civilization fell, we can now ask, given this specific environmental challenge, how did its people respond? Why did those responses succeed or fail? This honors the full complexity of history. It recognizes that our ancestors were not passive victims of their climate. They were active participants making choices within the boundaries set by their world. Their triumphs and their collapses were a dialogue between their ingenuity and the planet's changing rhythms. The ice has given us one side of that conversation. Our task is to listen and to reconstruct the other. The story in the ice is still being read, and new chapters are being added fast. The tools we use to read this frozen library are changing. They're pushing what we can see. There's one called continuous flow analysis. Instead of cutting a core into thousands of pieces for the lab, you take a thin sliver of ice. You melt it in a controlled stream, and as that ancient water flows past a bank of sensors, it gets analyzed in real time. Impurities, chemicals, dust, all measured instantly. Down to a resolution of millimeters. That's like going from reading a history book one chapter at a time to scanning every single sentence, every word in a continuous scroll. It shows events we might have missed. A single volcanic eruption might not be one spike. It might be a complex series of pulses. A short, sharp drought might appear in the dust, lasting only a few years but with a devastating local impact. It's a high-definition view of the past, the climate's fine print, and the search is pushing deeper in time. Literally, in Antarctica, teams are looking for the Holy Grail, a continuous ice core that goes back 1.5 million years. The oldest continuous core we have now goes back about 800,000 years. Finding older ice is crucial because around 1 million years ago, the Earth's climate rhythm changed. The pulse of ice ages shifted. It went from a cycle of about 40,000 years to one of 100,000 years. Why, we don't fully know. A core that spans that transition could hold the answer, locked in its bubbles. Drilling for that ancient ice is a monumental challenge. The ice flows like slow molasses under its own weight. The oldest layers near the bedrock can be distorted or melted. scientists are surveying the most remote, stable domes of East Antarctica. Places where the ice is thickest and the flow is minimal, to find a perfect, pristine record. Recovering it would be like opening a volume from an earlier epoch. One we've only guessed at. Then there's the most intimate frontier, the biological traces. Beyond pollen and dust, the ice holds fragments of ancient DNA. Genetic material from plants, fungi, bacteria, even viruses frozen in time. New ultra-sensitive sequencing techniques are starting to let scientists sift through this genetic soup. The potential is breathtaking. We could reconstruct past ecosystems in detail, knowing exactly which plants colonized the tundra as glaciers retreated. We might detect the genetic shadows of animal populations that migrated with the climate, and with extreme caution, researchers could identify ancient pathogens. The very microbes that may have caused historical pandemics, finding a virus frozen during the time of the Justinian plague or the Black Death, that could tell us not just about the climate conditions that let it spread, but about its evolution, its origin. This turns the ice core from a climate log into a frozen biosphere, a snapshot of the web of life itself, preserved alongside the temperature data. These emerging technologies promise a richer tapestry. We won't just know that a drought occurred, we might know what plants died first, what microbes flourished in the dry soil, what genetic adaptations were present in the region's life. We'll see climate history not as a single line on a graph, but as a multidimensional story. Atmosphere, life, and human society interacting in real time. The field isn't static, it's accelerating. Each technological leap is like polishing the lens of a telescope, letting us see further back in greater detail. The frozen archive still has profound secrets to whisper, and we are just learning how to listen to its faintest, most ancient voices. We have an archive, a collection of clues, different voices from the past, the economic whisper of lead, the dry sigh of dust, the acid scream of volcanoes, the biological breath of methane. Each one tells part of a story, but when you listen to them all together, a deeper pattern starts to form. It's not about any single event. It's about the chorus, the way these stresses can layer, one on top of another, until the weight becomes too much. Think of a civilization not as a monolith, but as a complex system. Like a bridge, it's engineered for certain loads. It can handle heavy traffic, a strong wind, even an earthquake of a known magnitude, but then you get a slow, relentless corrosion, weakening the steel, and then a flood, undermining the foundation, and then a tremor hits. The bridge was designed for stress, but not for that specific combination. Arriving in that sequence, the ice core record shows those multiple loads. It shows the corrosion, the floodwaters, the seismic wave, all written in different inks on the same frozen page. Take the classic case: a society faces a prolonged drought. You see it in the dust layers. Its agricultural surplus shrinks. The population feels the strain. Social tensions rise. The government's legitimacy, tied to providing stability, begins to erode. Then a massive volcanic eruption happens. Its sulfate spike is clear in the ice. It plunges the region into a volcanic winter. Crops fail utterly. The weakened system, already operating on the edge, receives a shock it cannot absorb. Famine spreads, central authority collapses, people disperse. What might look in the archaeological record like a sudden collapse was, in fact, the final step in a long cascade. The volcano wasn't the cause, it was the trigger. The cause was the vulnerability, built up over decades of environmental pressure, but the pattern isn't always so dramatic. Sometimes it's slower, more insidious. The ice shows a gradual climatic shift, a cooling trend, a slow drift toward aridity. Over generations, this shift pushes against the limits of a society's adaptation. Their farming techniques, their water management, their entire way of life, it was all calibrated for a different world. They might innovate, they might try to adjust, but the margin for error gets thinner and thinner. Then a political crisis arrives, a war, a disastrous leader, a rebellion. In a stable environment, the society might have weathered that storm. But in a state of chronic environmental stress, that political shock becomes the breaking point. The ice core gives us the background of that chronic stress. The long-term pressure that made the political body so brittle. This is the crucial insight. The frozen archive moves us beyond simplistic stories, invasion or foolish kings or mysterious plagues. It doesn't replace those human factors, it contextualizes them. It shows the stage upon which those human dramas became tragedies. A drought didn't cause a war, but it could make conflict over scarce resources almost inevitable. A volcanic winter didn't invent a plague, but it created the conditions, famine and social dislocation, that allowed a pandemic to burn like wildfire through a weakened population. So is there a unified theory of collapse? The ice suggests not a single formula, but a recurring theme. Civilizations are systems built for resilience within a certain range of conditions. Their collapse occurs when multiple stressors, often environmental, push the system beyond that range, and do so faster than the society can adapt or reinvent itself. The environmental data provides the often missing variable. It turns the question from why did they fall to how did they manage to last as long as they did, given the challenges they faced. The final lesson from the ice is about interconnection. It shows that the fate of a city in Mesopotamia was linked to dust storms over Arabia, that the prosperity of Rome was measurable in the Arctic, that the silence of a Greenland farm was connected to ocean currents, to hemispheric temperature shifts. Our ancestors lived in a world they perceived as vast and disconnected. The ice reveals it was always a single, interconnected system, and their survival or their disappearance was a dialogue with that entire system, a dialogue we are now, for the first time, able to hear in full. Which leaves one final reflection. We are not outside this story. We are writing the next layer of ice right now. The frozen library has spoken. It's a history written in layers of ancient weather. We've seen Rome's economic pulse in lead dust that reached the Arctic. We've felt the global chill of volcanoes in spikes of acid. We've seen the emptiness after pandemics in a sudden drop of methane. These aren't just data points, they're echoes, environmental echoes of human joy and ambition and struggle and silence. The lesson from this icy archive is consistent. It's profound and it's humbling. Across millennia, across continents, the most common threat to a thriving civilization wasn't a foreign army. It wasn't a failed ideology. It was a rapidly shifting environment, a change that arrived faster than a society's capacity to adapt. The Mayas' drought, the Norse's creeping cold, the Akkadians' dust, each was a challenge that outpaced their cultural reflexes, their technological reflexes. Their worlds were built for a certain climate. And when that foundation moved, the structures atop it often couldn't hold. This knowledge from the past isn't a verdict on those who came before. It's a lens. A way to see our own moment with a terrifying perspective, and perhaps a clarifying one. We are now the authors of a climatic shift. The graphs from the most recent ice layers show a line shooting upward. A change in speed and scale that has no parallel, not in the 800,000-year record. We are conducting an experiment, an unprecedented experiment with the only atmosphere we have. The frozen archive shows us what happened to societies that faced lesser changes with far less understanding. We have the understanding, we have read the book. The question is whether we will heed its most urgent chapter. So let this journey through frozen time be more than an exploration of mystery. Let it be a source of empowerment. The past does not have to repeat itself. We are not passive characters anymore, not in a story written by natural forces alone. We have become a geological force ourselves. With that power comes a profound responsibility and an opportunity. The same ingenuity that lets us decode warnings from ancient ice, That ingenuity can be directed toward building resilience, toward adaptation, toward rewriting our relationship with the planet. The lessons of dust and acid and gas are a stark warning, yes, but they are also a call. A call to write a different ending for our own chapter in this long story, this intertwined story of humanity and Earth.